we were discussing about Laplace transform, very interesting topic and useful practical applications, Laplace transform. Of some standard signals and some properties. And for example, we found out last time Laplace transform of a unit step function is equal to 1 over s, and then Laplace transform of e to the power, no, not e to the power at, in general Laplace transform of x t I will denote it by capital X s, and the Laplace transform, if you multiply this function by, if you time shift the function x t into u t, mind you, because one sided Laplace transform we are doing x t into u t is u t, that is why. So, x t into u t is x s, then x t minus a into u t minus a shifted version, this will become same x s without a, but multiplied by e to the power minus s. That is what we have seen. Okay. Now, there are next thing is, if a function is multiplied by e to the power a t, suppose x t has a Laplace transform x s, this time I will write it like this. This is a unique pair. X t in time domain, it has got a Laplace transform x s. If x s is known, I will be able to find out x t inverse way. Inverse way I have not talked about till now, but that will be done from the table as we will proceed further. So, x t is x s, then I say that what is Laplace transform of e to the power x t into u t, Laplace transform of this is this, then what will be the Laplace transform of e to the power a t? X t u t. That is what I want to find out. Got the point. So, we start from fundamental. So, I say that Laplace transform of e to the power a t x t into u t, this multiplication of u t allows you to use the limit of integration from 0 to infinity. You must have understood by this time. So, it is equal to e to the power minus s t into this function e to the power a t. This is the function I am writing, e to the power a t x t, and this u t I am not writing, because between 0 to infinity u t is 1, it is one and the same thing, into d t. This is what I have to do, is not. So, this integration is equal to 0 to infinity e to the power minus s minus a into t into x t into d t, is not. That is what you will get. Now, obviously, this I have got the result 0 to infinity e to the power minus s minus a t x t d t. Now, but I know that Laplace transform of x t is x s, which means that 0 to infinity x t e to the power minus st into dt. This integral is excess, is not? So, here instead of s it is s minus a. So, this must be written as the same excess, but s should be replaced by s minus a, that is all, there ends the matter. E to the power, if it were minus pt, I would have written x of p. I think you have got the point. So, essentially what I mean to say, if Laplace transform of x t is excess, then if you multiply this function with e to the power a t x t and all are causal signal multiplied by u t into u t, even if I forget e, I mean that. So, e to the power a t x t u t will be nothing but x of s minus a, whatever was a you multiply with, replace s by s minus a. For example, Laplace transform of u t I have already calculated, it is equal to 1 over s. Then I am saying that Laplace transform of e to the power a t u t will be nothing but replace s by s minus a, this a. So, if you multiply function with exponential e to the power a t, its Laplace transform will be e to the power a t into u t. So, practice it and you can find out anything. Okay. So, this is the thing. Now, some properties. So, we have seen for a given function, if Laplace transform is known, if it is time shifted, how to calculate the Laplace transform. If there is a given function, causal function, whose Laplace transform is known, if it is multiplied with e to the power a t, then what will be its Laplace transform? That also we have calculated. We have seen that. After now, what will be the Laplace? Now, these are now topics which will be directly applied to the solution of differential equation. The idea is, if suppose I say if Laplace transform of x t, obviously u t is excess. I am repeating x t u t, you understand. It means that the value of this whole function x t u t is equal to 0 for t less than 0, and it is equal to x t for t greater than 0. That is clearly understood. So, if this is the thing, then what will be Laplace transform of dx dt? That is the question. Now, as you can see, the Laplace transform of dx dt of this function. So, here is a function x t into u t, if you sketch it, it will have its say only for t greater than 0, for t less than 0 it is 0. Therefore, dx dt for t less than 0 is 0, a constant 0 value, its differentiation is 0. So, the dx dt also does not exist for t less than 0. Therefore, when you differentiate a function x t u t, it also become a causal signal like here. Therefore, I can start from this thing, that Laplace transform of say dx dt into u t. U t is ensured here, because x t u t, that is what I told. So, dx dt will be 0 for t less than 0. It will be equal to this integration, you have to calculate 0 to infinity e to the power minus s t into the function, that is dx dt, into dt. Is not Laplace transform of dx dt I want to find out. So, this will be the thing. What is known? Laplace transform of x t is known. Now, this I will write it as integration of 0 to infinity. First, I will write this function dx dt into e to the power minus s t dt. Now, this I will integrate by parts. This is the first part, first function, and this is the second function. Okay, this is correct? No, I will take. And let me see if something comes out wrong, we will see. So, this is the first function if you take. So, first function into integration of the second, then differentiation of the first function, then d2x dt2 will come. So, what I will do is, I will treat this you cancel out, I leave it here, and this I treat as first function. And this as second function. So, this one will be first function into integration of the second. What will be the integration of this second function? It will be x t. First function into integration of this second, and then I have to put the limits between 0 to infinity minus integration of differentiation of the first function, that is minus s into e to the power minus s t into integration of the second, that will be x t and dt. This will be the thing. And this is s equal to 0 to infinity. Now, here comes this first integral. Once again, this is equal to e to the power minus s t into x t to be evaluated at t equal to infinity minus e to the power minus s t into x t to be evaluated at t equal to 0. This will yield these two terms and this will become s. This s can be taken outside because you are integrating with respect to time. So, this will become 0 to infinity e to the power minus s t x t into dt. This will be the thing. Now, once again, if I want to evaluate this function for t equal to infinity, and once again as I told you, this s means minus sigma plus j omega into t e to the power. This you have to evaluate at t equal to infinity. What will be the fate of this term? Fate of this term will be, so far it is equal to e to the power minus sometime before I told this argument, once again I am repeating, j omega t. As t tends to infinity, no matter what it is, what will be the magnitude of the e to the power j omega t? Even if t is very large, can it be infinite? No, because it is cosine omega t plus its amplitude is 1 only, bounded by 1. But as t tends to infinity and sigma is correctly chosen as ROC, then this fellow, that is sigma is a positive number, this fellow will tend to 0. So that is why this will become 0. this first term, but this term put t equal to 0 straight away, e to the power 0 1, and this is x 0. And so far as this term is concerned, it will be s into x s, is it not? So, Laplace transform of dx dt is nothing but s into x s minus x 0. This is the thing, ultimate final result. Got the point? Therefore, you see the as if it looks like this d dt term is replaced by s with the Laplace transform x s, and it becomes differentiation becomes an algebraic multiplication of s into x s. This is the first thing to note, because after all in circuit analysis with energy storing elements we have to face differential equations, and we know from our previous studies how it can be done by classical way, that is different story. Now, here is something very interesting, differentiation of a given function. If you take its Laplace transform, it gives rise to some sort of an algebraic equation. What is x 0? X 0 is the initial value of the function at t equal to 0. So, one can extend this idea. So, we have seen that Laplace transform of x t is equal to x s. With this we started. Then I am saying Laplace transform x t into u t, always I forget, is x s. Then Laplace transform of dx dt we have just established, it is equal to s into x s. Okay? X into x s, this x s minus x 0. This is the value of the function at t equal to 0. So, as if this d dt has been replaced by s, like in sinusoidal phasor notation d dt was replaced by j omega. Laplace transform is a more general frequency, not only j omega, but e to the power sigma plus j omega. One can find out such a correlation, I mean think in terms of that correlation, but this is the story. Now, therefore, Laplace transform, let me not spoil it. So, we have got this one dx dt. This is one interesting result. What about higher order derivatives? Then Laplace transform of d2x dt2, suppose second order differential term, it will be how much? Answer is very simple. Now, I have established this, no one can stop me. For example, I will say, okay, look here, Laplace transform of d2x dt2, you can write it as this. Is not Laplace transform second derivative, I can write it like this. So, here this is the function whose but Laplace transform of dx dt is known, this to be this. So, what it will be? It will be s into Laplace transform of dx dt and minus of functional value of dx dt at t equal to 0, is not, this will be the thing by this argument. So, here x is taken care of by dx dt, its Laplace transform is known, yes, I have right now derived s x, s into s x minus x 0. So, d dt of this function will be Laplace transform of dx dt, this one, minus the initial value of dx dt, that is this. So, this will be equal to, in short I can write Laplace transform of dx dt minus, this is in short I will write it at x dot at t equal to 0, x dot means dx dt. Then s into Laplace transform of dx dt will be how much? S into x s minus x 0 and then minus this x dot 0, and this, if you open this bracket, it will be a square into x s minus s into x 0 minus x dot 0. So this is the thing, you see Laplace transform, I will say then d2t dx d2x dt2 is equal to this one. So one can go on extending this to find out the Laplace transform of differentials of any order. For example, now after this I will say I will not derive, but I will just I can write down. Can you write down this dqx dt2 dt cube? Yes, I can. It will be s cube x s minus s square x 0 minus s x sorry x dot x 0 test s x 0 minus x x dot 0 and minus x double dot 0. This will be the order in this s square into x s minus, because in in a third order differential equations 3 boundary conditions will be necessary, x 0, x dot 0, x double dot 0. Second order differential equation 2 boundary conditions will be necessary, x 0, x dot 0. So anyway, so this is one of the very important finding so far as Laplace transform is concerned, that is differential terms. Okay, fine. Acha. Now another interesting thing is, so then the next another interesting property I will tell, that is naturally comes as the integration. Although we will not be using integration, because I told you whenever I will be solving circuit problem, better write it in terms of differential equations, no integral differential equations. But nonetheless, it is worth noting what happens, that is the second thing is, if x t Laplace transform of x t into u t is equal to x s, then the question is what is Laplace transform of integration of x tau d tau 0 to tau 0 to t. Mind you, this way why I am writing, because integration you want to take the function, take the integration, but ultimately it has to be a function of time. So this integration will confirm that. When you carry out this integration, you will get the area under the curve up to time t. So what is the Laplace transform of this one? I want to find out. Clear? The answer is to find out this, and this is known. First step what I do is this, let this integration 0 to t, this function whose Laplace transform is necessary is this one, x tau d tau, and obviously it will be a function of time, this t, let this function be g t, let this be this. Then what I am trying to calculate is Laplace transform of GT. I am trying to finding out where GT is this. Obviously, if GT is this, then dg dt must be equal to xt. Integration of this function is gt. So, if you differentiate this, you will get xt. So, dg dt is xt. We note it down there. Then gt, and of course, this is multiplied by ut, that stuff remains, which allows me to integrate it from 0 to infinity, and this is equal to e to the power minus st into gt into dt, is not? That will be the thing, e to the power minus st dt. Now, here what I will do is this I will write it as, I will treat this gt as first function and this as the second function and integrate it by parts. So, this will be equal to first function into, so this is the first function, treat it, and this you treat it as second function and integrate by parts. So, first function into integration of the second, that is e to the power minus st by minus s. This will be this one, and this you have to evaluate at t equal to 0 and infinity, take that difference, minus integration of 0 to infinity, differentiation of the first function, that is dg dt, into once again integration of the second, and that is into dt. Got the point? Now, this so this is once again is this one gt into e to the power minus, which I will not further elaborate now, minus s. This I have to evaluate at t equal to infinity, and the result I know it will be 0. Why? Gt is a reasonable good function, nothing like that. So, at t, as t tends to infinity, that minus sigma t will vanish, no matter what is the value of functional value of gt at t equal to infinity. This will make it 0. So, that will be 0. In the same way as I have explained it, minus this I have to evaluate at t equal to 0, that is very easy, 0 divided by minus s, is not? Put t equal to 0 and get this, and minus of integration of 0 to infinity, dg dt is nothing but xt. So, xt, this one is xt. So, write xt e to the power minus st, and this minus 1 over s will come outside, make it plus, and this s, because you are integrating it with respect to time, not with respect to s. So, this s term can be taken outside. Now, the question is gt is this. So, what is the value of g 0? So, since gt is equal to, since gt I am rewriting 0 to t x tau d tau is what? Area under the curve, and g 0 is 0 to 0, that is no area will be covered. So, this g 0 is any function if you integrate from with same limit, what it is 0. So, you will be left with, so this term is 0 because e to the power minus sigma t goes to 0 as t tends to plus infinity, and this term g 0 is 0. So, this is also 0, it goes, and you will be left with only with this term, and this by definition x t into e to the power minus s t dt is nothing but excess. So, excess by s. Therefore, we say that finally Laplace transform of 0 to t x tau d tau will be nothing but excess by s, where excess is nothing but the Laplace transform of x t. Got the point? Or where excess is equal to Laplace transform of x t. So, this is the one thing. Another small result I will just tell. So, these are some of the properties of Laplace transform and how it can be used. One last property I will just show you. If I say, if this is one line proof, if Laplace transform of a signal x t u t is equal to x s a, what will be the Laplace transform of this function r x t u t. You recall t into u t is r t, that ramp function. So, if you multiply a function with a ramp function, what will be its Laplace transform we want to find out. Now, to do this the proof is very simple and interesting way it can be done. We know that excess, we know that excess is equal to 0 to infinity e to the power minus s t into x t into d t. Laplace transform of x t into u t is this, we know that. Now, you see what you do, you differentiate both sides, differentiate both sides with respect to s, So, you will get dx ds here. On the right hand side, integration means summation of small numbers, infinite whatever number. So, and those terms has only e to the power function of s is this term. So, differentiation of this term only. So, it will be minus s into e to the power minus s t. X t will be treated as constant, you are differentiating it with respect to s. So, I can write it like that. So, dx ds, oh I am so sorry. So, if I differentiate it with respect to s, so it will be t, is not, t should be treated as constant minus t, is not. So, this will be equal to minus this integration sign can be taken outside and it is e to the power minus s t into t into x t into d t. Or I can say, if you bring the minus side to the left, I can say e to the power minus s t into t into x t dt integrated from 0 to infinity is equal to minus of dxs ds. Therefore, this is also interesting to note that if you know the Laplace transform of a function x in terms of s, then the Laplace transform of the same function when multiplied by t will be simple differentiation of that function preceded by minus sign. I leave it to you to find out, only indicate that, so that you can do Laplace transform of, suppose I say t square x t. If I multiply it by twice, I will not find out a general formula t to the power n x n, okay, that can be done, but I am telling you the idea. This is the thing, is how much if Laplace transform of x t is equal to x s. Suppose this is known, then what should be this? Then I will go like the previous differentiation formula for higher orders. I will write it like this: Laplace transform, you are asking me for t and this function t into x t. You group these terms, is how much I have to find out. This will be equal to, we know from the previous result, what was the previous result? Previous result was, if this is this, then Laplace transform of t x t is nothing but minus dx by ds. That was the previous result. So, here it should be minus, so I have Laplace transform of t x t is known, which is equal to minus dx ds. Therefore, it should be minus dds of the Laplace transform of this quantity. This quantity Laplace transform is minus dx ds. So, put it here. And which will come out to be d2 x s ds 2. So, Laplace transform of t square into x t, u t of course is there, is this one. Anyway, I stop here today, and next class will be very interesting. We will be applying this whatever we have learned to solve network problems, and there we will see Laplace transform method. If we adopt, it does several things. It will essentially convert the differential equations into algebraic equations, and also the initial conditions will be automatically inherent in the Laplace transform expression. For example, Laplace transform of dx dt, as we have seen, is nothing but s into x s minus x 0. What is this? This is small x, no capital X. This is the functional value at t equal to 0. More on this in the next class. Thank you. Hopefully, you are following me. Hope you are following me. Thank you.